Yeah, fine. Let us start today's lecture with a nice example which is based on concept of current electricity. And here we will use the concepts like the concept of current density J written as sigma into E vector, right? And the concept that potential difference across the two faces can be written as current into resistance. So I'll use both the concepts. This is all of us understand that the core concept for Ohm's law is actually this format, J is equal to sigma E. And then the flux of current density is something which is interpreted as current. So technically speaking, when we talk about Ohm's law, basically we say that at any given point, if you take a differential area, the current density there is the conductivity into field which is present at that point. And I have clarified you that I look at I as the flux of J, flux of current density. And current density is proportional to E. So these things were there in my mind. So let's see how to approach the problem. The question says that there is this material which is anisotropic. That means the nature of the material in all the directions is not identical, right? And he says that in this two-dimensional plane, along the x, so let me draw it here, along the x and the y directions, the behavior is different. So along the x direction, remember x and y are lying in the plane of this object. So along x, along y, which are mutually perpendicular, we have different resistivities. So he's defining rho along the x direction as some rho max. And he's defining the resistivity along the y direction as some minimum value rho min. That I will use in the later part of the solution. That's fine. Now he says that there is a strip ABCD having a length of L. So you have been given this dimension. This is L. And the breadth of this strip is B. That is also known. Theta in this problem is very evident. Like it is making an angle of theta with the edge AB. So x-axis, like this angle is theta, and this angle is 90 minus theta, right? Now the question starts from this point. He says that if you apply a constant potential difference between these two faces, so if you apply that constant potential difference between face AD and BC, and that difference as such is somehow like V, by virtue of this effect, what will you develop between P and Q? So your question was, can we write the potential difference between point P and point Q? That is what we have to calculate. So as I'm solving this problem in two dimension, I'll go from the basic. Whatever electric field E is present. Now, once I want to solve this problem, first of all, I'll say that whatever field you have got in this problem, let us try to resolve it in X and Y. So this direction X, here I have got a direction Y. So I will say I've got an electric field along X. Let me call it as EX. And an electric field along Y. Let me call that as my EY. The components of field present in this body. So EX and EY. Now, because you have applied an external potential difference between these 2 points, I will say that there is some current density J vector which is present in the problem. Along there is a flux. So that flux is because of this battery which you have applied. So if I perceive that flux as a contribution because of current density, I can literally observe it like this, that my J has those components J cos and a corresponding component J sin. And because J was equal to sigma into E, And sigma I can write as 1 upon rho, 1 upon resistivity. So I'll write this as 1 upon rho y sigma into Ey. And this term I can write as sigma, which is 1 upon rho. So rho x into Ex. So I've got two equations for Ey and Ex as such. And now I know, I'll write here. Now I can say, let me now write the first equation in this problem. So I'll say the potential difference that this guy has applied between these two faces seems to be the field in that direction. So Ey cos 90 minus theta forward. So Ey sin theta plus Ex component forward is Ex cos theta, the net field, multiplied by the distance L. Now I can say, as we know, as it is given in the problem, that this is V. Now do one thing, you substitute your Eys and Ex's in terms of J. So your Ey is J sin theta into rho y into this term sin theta, plus your Ex is J cos theta rho x, and there is a cos theta term, and basically this multiplied by L is giving you this value V. Now I can say that from this equation, if I take J common out, I'm getting V upon L rho y sin square theta plus rho x cos square theta. So what I did, I used the very fundamental equation that potential difference is equal to, if fields are constant, I just took their components along that direction, and I say it is the net field along the direction, which is along the normal to the two faces, and multiplied by the distance. I got the value of J. Now what is our requirement in this problem? Our required quantity is, he is saying, you try to give me the value of Vp minus Vq. So I'll say from top to bottom, the net field that I'm getting in the downward direction is Ex sin. So I've got Ex sin, and then I've got a Ey sin 90 minus theta is Ey cos. So minus Ey cos multiplied by B. If I can find out this expression, I'll get my answer. Now let me try to write the expression which is desired. So what I'll do, our requirement Vp minus Vq can be written as B into. Now I need Ex sin theta term. So Ex can be written as J cos theta rho x sin theta minus Ey cos. And Ey is J sin theta rho y into cos. And already I multiplied it by B. So when I solve it, it seems like J will come outside. There is a B term. There is a sin theta cos theta term. And then there is a rho x minus rho y term. So what I am getting? I am getting JB sin theta cos theta rho x minus rho y. And J was known here, so I'll just substitute. So what will I get finally is V by L rho y sin square theta plus rho x cos square theta, that is my J term, into B sin theta cos theta rho x minus rho y. This is the actual expression for the answer. And if you look into the data of the problem, V, BL, theta, rho x, rho y, just check the data. L, P, theta, V, rho max, and rho min, which was given. In fact, that ratio term will come out on its own, because when you will solve this problem, rho x, rho y is not required, the ratio is required, and ratio factor 0.4 has been given to you. So you beautifully get the answer. It is actually a nice problem where generally we apply Ohm's law in 1D. And in this nice question, they've used the concept in 2 dimension and we got the result. So ultimately, the idea was that the student should be writing this equation properly. J is equal to sigma E. And when he is writing V is equal to IR, he should be interpreting it as the dot product of, like it should be interpreted as the dot product of minus E dot ds. ds is a differential displacement and you should be taking sigma or integral. So when I have written my V, desired V, you can observe that I've used that E dot ds along the length and then I observe the direction and obviously I will get the result. Right? All right. Let me take up the next concept today. So I'm taking problems from all these sections just to ensure that all the variety is considered in least amount of time. So next problem, I will talk about the concept of magnetic Gauss law. So Gauss law in magnetism and the concept of a half solenoid. So let us understand what we are trying to learn in this problem. This is a hollow cylinder on which turns are being wound in such a way that the number of turns per unit length on this winding is N, and the current that these wires are carrying is capital I. The radius of this solenoid, this is a half solenoid. There are 2 important things which we want to learn in this problem. First of all, we know that the expression of magnetic field in ideal solenoid is mu naught Ni. But we know that is valid only at the absolute center on the axis and if the length is large. Otherwise there is a term of cos theta 1 plus cos theta 2. So if you observe this carefully, first, like we should be able, what I'm trying to write first is the data that I need is agar they have given you a solenoid in such a way that it has got some finite length, right? They have got some finite length. Then if you want to derive an expression for magnetic field at any point on the axis, what we do? We take these angles from the end point. So basically you form a cone in 2D. So this semi-vertex angle of the cone is alpha, and the second end of the solenoid, again it will form a cone, and in 2D the semi-vertex angle is beta. So all of us have derived, in theory, we have studied this thing by derivation, and I'll also discuss how we derive. Like it is coming out as mu naught Ni by 2. If the current in these wires is I, number of turns per unit length is N, then it comes out as into cos alpha plus cos beta. So all of us understand, we go at a differential distance of x, we cut a differential element dx, then I get a ring. The field because of one ring is mu naught into I into r square upon twice of r square plus x square raised to the power 3 by 2. Then I multiply by n dx, the number of turns in the ring. Then I integrate from x is equal to this point to x is equal to this point, and I get this expression. Very fundamental derivation. All of us have done. Now, once I know this and I take this question, the question says, given all this, you go on the axis from the end point to a point which is at a finite distance x from the end. So we are sitting somewhere here, and then we move radially a very small distance r. So practically you are sitting here, right? And basically you can be sitting anywhere on this ring. So by 3D symmetry, we are talking about the magnetic field at this point. And he is very clear in this problem. He is very categorical that you go to this point, you go a distance x in the forward direction, and you denote your unit vectors by ex cap and er cap, and a very small distance r. So basically he is talking about this vector as er cap, and he's talking about unit vector in this direction as ex cap. So he wants me to calculate here. So I have just explained by symmetry, but if you want to write the expression vectorially, we have to have a unique point, and that point is P. So I'm interested in magnetic field B vector at point P there. And the problem is, I know the expression of magnetic field only in the axial direction. So this expression that I have written is either left or right, depending upon the direction of current. like clock or anti-clock. But this is giving me magnitude along the axis. So let me just explain. So if I presume that a guy standing here is observing these currents counterclockwise, if I presume that, then the field in the x direction will be coming out. So what I can say is at this point, there is some field along the axial direction, that is dx, and I go a bit up. So because r is very, very small in comparison to x, my magnetic field in the x direction nearly remains the same. So it nearly remains bx, but I gather a radial field, which is actually br. So my BP vector, which is my answer, is bx ex cap along the axis. And then there is a guy br in the radial direction er cap. This can be my answer if I can derive the expression of bx and br properly. That is what is desired. Now, as far as first equation bx is concerned, I could have used this formula directly here. I could have said that from this end, there is an alpha angle I will draw. I'll use a different color for it, right? And from the other end, like which is at infinity, if you draw that angle will tend to 0. So in this combination, this is a mirror image of this theory which I have written. So technically, only the direction changes. So beta is tending to 0, roughly. And that alpha can be written like the angle that I have shown here. This angle can be represented as your alpha. So what you'll get is bx is mu naught ni by 2, and use that term cos alpha plus cos beta. So cos alpha here is x upon that distance, which is root of hypotenuse term of this right angle triangle. So that is root of x square plus r square. And cos beta is coming out as 1. Cos beta is coming out as 1. So now I'm ready with my bx. The complete issue lies with my br. This term is not known, this is known. So what will I do now? So now I will try to apply the Gauss law in magnetism. Gauss law in magnetism says that if you take a closed surface, over the closed surface, integral b dot ds or dA, whichever term you use, area vector, that should be equal to 0, because in magnetism, the net flux which will cross a closed loop will be 0, because field lines will always form closed loops. Or you can say the net magnetic monopolic charge will be 0. They always form dipoles, so we know that. So what I'll try to do now is, I'll try to make a Gaussian surface in magnetism. So when I'm sitting here, let me draw here itself. I'll go a distance dx forward, and I will draw a Gaussian surface. So I'm sitting here at x. I'll go a distance dx forward, and we'll try to apply Gauss law over this small cylinder of radius small r and length dx made at a distance of x, right? So let us try to apply over this volume. So on the surface, what do we observe? Equation number 2, what do we observe? So I have got a BR here. So I'll have these BRs. I'll have these BRs which are coming out. So the flux from the curved surface area and the base surface area, the lid areas, that should be equal to 0. So from the curved surface area, it seems the flux is B as function of R radially outward everywhere on the curved surface area into surface area, which is 2 pi small r into dx. 2 pi small r into dx. Plus, from the base surface area, what will happen? Some field will enter in like this, because I have got some B as function of x. So by simple calculus, I can say if I move a distance dx forward, I'll have a new b here, that is b as function of x plus db as function of x. So here b as function of x is entering, and here what is coming out is this. So the flux from the base surface area, this flux which will come out will be positive. So positive bx plus dbx multiplied by this area, whatever you have taken, like pi r square, r is small. And there is some flux which is entering from this side. So it is negative because it is entering by convention. So Bx into pi r square. This much is the total flux from the base surface area. This is from the curved surface area. So net should be 0. Now just try to compile these terms properly and see what you are getting. So let me write my second equation here. Now things are streamlined properly. So I am getting b as function of r into 2 pi small r into dx. And then I'm getting these terms here. So bx into pi r square will cancel. So I'll have a dbx into pi r square. That term is coming out as 0. This and this. So pi r and pi r will cancel. So basically, now I can say from these two equations that my br is minus r by 2 times d by dx of b as function of x. So it is minus r by 2 and db by dx. And because b is known to us, it is minus r by 2. I'm just differentiating this term. So I got mu naught ni by 2. I got the derivative of this term 0. Then I have to differentiate this. So just apply the quotient rule gradually, slowly. So I got denominator, so x square plus r square, right? Then root x square plus r square, x1 minus x, derivative of this. So by twice of root x square plus r square, and then multiply this by 2x. I multiplied that by 2x. So very categorically, if you observe, you are ready with your expression. Now, take care of this thing that that capital R and small r is not the same. Just be careful. So it is minus mu naught n capital I r by 4. And what are the terms I am getting here? This 2 will cancel out. It is small x square plus capital R square raised to the power 3 by 2. And it is r square. Like x square plus capital R square minus x r square. So if you observe now, you have got your expression in terms of small r, capital R, and x. Now I know the value of br. I know the value of bx. Now, only thing that is expected from the student is he substitutes bx and br properly, br from the lower side properly, and just write this vectorial expression, and that is the answer to the question. So some fundamental ideas we used, like you know a non-ideal solenoid, you know the field on the axis, you don't know the radial field just outside. So use the expression of the axial field to find out the radial field using the Gauss law in magnetism. So this is the concept that I've used in the problem. Okay. Let me move on to a nice problem on ray optics now. This is very interestingly put up in this question. If you read this problem carefully, the combination is very nicely put up from ray optics. Let me explain what he's trying to do here. He's saying that there are a large number of thin converging lenses. So these are the thin lenses which are placed back to back. So large number of lenses. So thickness is small and they are distributed at a very small distance per unit length. Everyone is having a focal length of f. All these converging lenses are having a focal length of f. They are kept at equal distances of L from each other. L is very, very small, so that their optical axes coincide. And the distance L is negligibly small, wo sab clear hai, in comparison to the focal length. Now let us look into the core problem. He says, a light ray is made to be incident parallel like this at a distance of h. Now, because these lenses are stacked very close, that light ray will follow a unique path. The question is, while this ray crosses through all these lenses, which path will it follow? And can you write the equation of the path of ray? Remember, this is a very, if not the same question, this type of question is very probable in a top level examination. So whenever a tough question from physics may come in optics, these ideas are the ones which can be used. That the path of a ray, once for the first time, if you remember properly, 1995, the first time they gave a question which everybody knows now. They gave mu as a function of some y, and then they wanted you to derive the expression for the path. But this is just a typical combination of the same concept, because here mu is not varying. The function of mu is not given directly. Instead, they have given you lenses. So you have to convert the problem optimally. Now, how can I solve this problem? My concept is, like, if this is my x-axis, y-axis, I want to analyze this ray at a general point. So I want to take a general point on the path of the ray, and let's say that point is x, y. Now, while that ray is passing from that general point, I don't know the curve. It is crossing some lens or some combination of lenses. And at that point, I don't know the angle at which the ray is hitting the lens or the set of lenses. Now, let me be very clear here. If I'm standing at x, I will be analyzing everything over a length of dx. Now, this is not the lens. It's just a way of hypothetically expressing that thickness dx. So I am interested in that dx. What happens here? And that ray which reaches this point x, y, reaches here at some angle with the horizontal. So I can treat this angle, let's say, as alpha, maybe. And what is going to happen is, as the ray appears through two refractions and it comes out, so I'm showing the effective deviation. I'm saying this angle becomes alpha plus d alpha. D alpha is the further deviation of the ray. Now, let me be very clear. All of us understand the concept that whenever a ray hits a thin lens, let's say this is a ray, this is a thin lens, and a ray hits it at a distance of h from the principal axis, then after two refractions, like if you extend the first one and the last one, you understand that there is a deviation delta, and the deviation is h by f, right? F is the focal length. So I am not showing this part. I am directly supposing that they are merged at this point. So I am directly showing this, and delta is h by f. That is for a ray which is coming parallelly. And because the ray is initially coming parallelly, I am just using this concept here to tell you the amount of deviation. So I'm saying that the deviation that has happened is d alpha, and d alpha should be equal to the height of this point, which is y. So y divided by, if this would have been one lens, I would have taken f of this shaded lens, the shaded lens. But the problem is in dx thickness. Now the problem is in dx thickness, what exactly is the focal length? Like, can I tell you the focal length f, instead of shading again and again, let me write f net in dx thickness. So if I can write that f net in dx, I'm done with the problem. Now I'll use the concept of optical power. I know if you keep lenses back to back, there's a concept that 1 upon f effective is basically sigma over I 1 upon fi. I'll try to use this concept over that thickness of dx. So I'll say my 1 upon f net in that thickness is 1 upon f plus 1 upon f. So luckily, all the lenses are having the same focal length. So 1 upon f into number of people, number of lenses in that small dx. Now he has said that for every L distance that you move, you get one lens. Between two consecutive lenses, the distance is L. So for every L, you get one. For 2L, you get the second one. So in dx, how many will you get? So this will be dx divided by L. You divide dx by number of intervals of L. Those will be the number of lenses. And for all lengths, 1 upon f will come. So you'll get multiplied. I'll get my f net. And now by by first and second, I'm in a position to write the deviation of the ray T alpha is equal to y into this 1 upon f net, which becomes dx upon L into f. L and f are constants. So I got a nice third equation in the problem. Now, my concern somehow is L is given, F is given. If you observe, this H is also given. So I need an equation in y versus x. That is how I define my path of the ray. So I need y versus x. So somehow I have to eliminate this term d alpha. Now I know that if I'm at a general point on a curve, I'll use the equation of the slope of the tangent. So dy by dx can be written as tan of, so if this initial ray would have been extended, his angle is alpha from this side. These are alternate angles. So this angle is 180 minus alpha. So the slope of this line is tan of 180 minus alpha. And that becomes minus tan alpha. And now I can say, because these deviations are small, we are considering paraxial rays, this tan alpha, sin alpha, or alpha can nearly be the same at that location. Because you are taking small aperture paraxial rays. Your H is not so large. So basically you are somewhere here. So everything that is happening over all these derivations that I'm using is for small aperture paraxial rays. So I'm not mentioning it here again and again. But if this problem comes in JEE examination, they will mention it, because we are writing theory for small aperture paraxial rays. Now what happens is, so I got my dy by dx is minus alpha. So I needed d alpha. So I would have written this term again. So how will it come out as? So d2y by dx2, if you do, it becomes minus d alpha by dx. I have taken d by dx both sides. And here also, d alpha by dx is coming out as y by lf. So from this third, and from this equation that I have written here, if I just eliminate d alpha by dx, d2y by dx2 is beautifully coming out as minus 1 by lf multiplied by y. Now this is my crux, right? I have got a perfect equation, which is telling me that y will be sinusoidal. And this term I will presume as some omega square. So I can write my root y is equal to some constant into sine omega x. I could have generally written it as a sine omega x plus phi. This is the root of the second order differential equation. Omega is known to me. Now the concern is what is a and phi, but you knew that at x is equal to 0, y was equal to h, and which is maximum also. Or you can say mathematically that dy by dx at that point was equal to 0. So at x is equal to 0, you have got two conditions. If you put those conditions, I'm directly using it, y can be written as h cos omega x. Y is equal to h cos omega x satisfies the condition that, the boundary condition that at x is equal to 0, y is h, and at x is equal to 0, dy by dx is also 0. By this, and omega is known. So I could have said that it is h cos omega x, and omega as such was 1 by root lf. So now things are in streamline. So the answer to the path of the ray should be y is equal to h cos omega. Omega is 1 by root lf multiplied by x. So that is the equation that the ray is going to fall. Now, if you observe the concepts that they have used, you can understand they have mixed everything. They've used the concept that a student knows the expression of f net. They presume that you can write the f net for a dx length, because for every L length, another length will come. They've used the concept that delta is equal to h upon f for a ray which is nearly paraxial. So I've used the concept of deviation of a ray by a lens and a set of lenses. Then everything falls in place and you get your answer correctly. So just you need to ensure that such kind of concepts are known to you, because they can always ask small
Sir,
problems. Yeah,
can you once explain the F-net part, sir?
definitely. What I've said is, if I separately give you few lenses together, like if their lenses kept back to back of any shape, you know that the net power, that is 1 upon f net, is equal to 1 upon f1 plus 1 upon f2 and so on for all the lenses. Now, because I have to calculate for dx, I said 1 upon f net is 1 upon f, 1 upon f, 1 upon f, because all of them are having same f, f, f. In my case, everybody was symmetric. So only concern was the number of lenses. Number of lenses. So how I calculated, I said for every L distance, you get a new lens for another lens. So if you move 2L, you get 2 new lenses from this point. So for every L that you move, you get 1 new lens. So by unitary method, one you move, you will get 1 upon L lenses. And dx, if you move, you will get dx upon L lenses. So dx upon L is the number of lenses, right? So I wrote 1 upon f into number of lenses, and number of lenses was dx upon L. So basically, I got my answer as 1 upon f into dx upon L. So if you observe, that's what I've written, number of lenses. So I've used the formula and I got my result. Okay, let me take a very Avinash, yes, you want to say something?
When we used the formula that lenses were not touching, we had a formula of 1 by f1 plus 1 by f2 minus d by f1 f2.
D can be used if the distance is prevalent there. These lenses are kept at nearly zero distance. So he has, because otherwise the ray cannot have a unique path. Let's understand that in real life, this ray will have points of non-differentiabilities, critical points. But the curve can become continuous only if those critical points are very, very close to each other. So in this question, when he says at equal distances, and he says L is negligibly small, so he is basically telling you that this distance is tending to 0. Otherwise, that curve can never be continuous. So basically, I've kept them at distances dx, where dx is tending to 0. So even in your formula, 1 upon f1 plus 1 upon f2 minus d upon f1, f2, if that d is very, very small, it only becomes 1 upon f1 plus 1 upon f2. So that's what we have.
In a situation, if the d was more,
then this question is not correct, because then we can only analyze segments of rays, not a continuous path.
I'm not asking about this question. If that formula was used, what will be our effective u, object distance?
We can find out, like, you want to find the value of u from a combination of lens?
Means first lens से अगर देखें तो अगर u डिस्टेंस है तो जब इफेक्टिव फार्मूला लगाने के बाद जो लेंस बनता है उससे कितने डिस्टेंस में होता है ऑब्जेक्ट?
उसके लिए पहले आपको, if let me derive, have you derived the result for the location of effective lens? Do you know that?
I didn't derive, sir.
No, so we have to do the basic thing. The first thing is, let me share a few ideas with you. That means that concept needs to be discussed. Whenever a ray comes, I'll give you all the basic ideas. If a ray hits a lens at a height of, let's say, h1, it deviates by some distance, it hits the another lens at a height of h2, then again it deviates and reaches somewhere else. So very fundamental derivation. This angle of deviation is delta 1. Here also it gets deviated by delta 2. Now what the teacher does is, how we derive it is, we will first go to the equivalent lens. So what I'll do, I'll extend this ray, initial, and the final emergent ray, and I'll intersect them here. So the answer to your question lies on the location of equivalent lens. So in books, we generally write a formula for, if this is f1, this is f2, the distance between them is d. So there is an equivalent lens location, which I will derive now. And there is an equivalent f also. So Avinash can, the answer to Avinash's question will be, if we can find out this location, and if we can find out f equivalent, we are done with the question. Then we can replace our system by a green lens, and you will get the optimal value of u for the object, whatever you want to do. So let me just derive it. Now what I will do is, this deviation here will be equal to, observe it carefully, it is delta 1 plus delta 2. This is delta 1, this is delta 2. This exterior angle is sum of these two interior, delta 1 plus delta 2. And luckily, the location where it is hitting is again H1. So I'll call this as delta net. So my delta net is delta 1 plus delta 2. What are the things I can write? This is H1 upon F net. Delta 1 is H1 upon F1. Delta 2 is H2 upon F2. Right? So I have to go step by step. And I'll also find out this value X. So there are two requirements. F net is required and X is required. X को मैं बाद में कैसे define करूँगा? It is the distance of the equivalent lens from the second towards first. So if in a problem X comes out to be negative, the equivalent lens will be forward. And if X comes out to be positive, it is on the left side of the second lens. Left of second lens. Negative means right of second lens. Just take care of this, because the expression of X can be negative also. Fine. Now, 1 upon F1 plus H2 upon H1 upon F2 is 1 upon F net. So that is what we will get first. Now I have to eliminate some of these terms. So let's see what equations can we write. Now just observe this small triangle here, right angle triangle, and take delta 1. And tan of delta 1 is delta 1. So delta 1 is coming out as H1 minus H2, H1 minus H2 divided by D. And then a student can say, sir, fine, delta 1 was also H1 by F1. So 1 upon F1 is equal to 1 minus H2 by H1, this term, whole divided by D. So H2 by H1 will come out as 1 minus D by F1. So first of all, we substituted here. So we got 1 upon F1 plus 1 minus D by F1 upon F2, that is 1 upon F net. So that was the first part of derivation, 1 upon F1 plus 1 upon F2 minus D upon F1, F2. Now, if you understand the geometry, you are searching for X, take tan of delta net. So I will directly use a different color. In 1 or 2 lines, you will get your answer. Write tan of delta net and write it as H1 minus H2 upon X. So H1 minus H2 upon X is tan delta net, that is delta net, and that is delta 1 plus delta 2 also. Now substitute. So X is coming out as H1 minus H2 upon delta 1 plus delta 2 is H1 by F1 plus H2 by F2, and divide this complete equation by H1, numerator and denominator. So you'll get 1 minus H2 by H1 upon what is in the denominator, 1 by F1 plus H2 by H1, H2 by H1 divided by F2. Now you know that H2 by H1 is 1 minus D by F1. So 1 minus D by F1, and denominator you can directly also write, because H1 by F1 plus H2 by F2 is directly H1 by F net. But only because I have separately taken this term, so I'm writing 1 by F1 plus 1 by F2, this is separate term, multiplied by H2 by H1, and that is 1 minus D by F1. Observe this carefully. In terms of, like, you can solve this, X comes out as D by F1 in the numerator, and denominator it is 1 by F1 plus 1 by F2 minus D by F1, F2. So basically 1 by F net. So once you get F net, you can directly say it is F net into D upon F1. Just substitute F net and F1 with proper sign. First of all, you calculate F net. Substitute F net here with sign. D and F1 are known. So you'll get X with sign. And then you will get the location, and then you will solve. So like this was one basic derivation. Let's go to the next fundamental problem. Here in this problem, I want you to think about the possible combination. It is based on geometry, but very nicely put a problem. Question says that there are 2 point sources. Now observe the question. They have given you an equilateral triangle and a centroid location. The data is such that there are 2 point sources of light. So there are sources at a distance of 24 centimeter apart. So that is given. And then they are kept near a converging lens. So now in the question, you don't know anything except for the possible locations. You know that there are some bulbs or point sources. You know that the distance between them is 24. They are placed near a converging lens. Then there is a lens in a plane containing optical axis of the lens and the diameter of the lens. If I simply put up this thing, what he is trying to say, it is like treat this plane of the page like the horizontal plane, and your lens is kept horizontally. So the diameter and the optical axis are lying in this plane. So you can perceive the complete system to be drawn from top, and your lens is kept in that plane. So the orientation of lens is in the plane. So that is given. Now in the given figure, location of sources and their images are shown by 4 dots. Now the problem is the combination is such that, like, for one position of object, you have got one image. For another possible position, you have got another image. So basically, there are 4 dots, 2 objects, 2 images. Right? The dots are 3 dots are on the vertices of equilateral triangle, and 4th is at the centroid. Now he has not given anything about the location of lens. Location of lens is not known to me. So problem is good. Like, what are the questions IT can ask in this problem? He can fundamentally ask that where is the lens for this possible set to be formed? What is the focal length? So my questions can be location of lens, I can ask. Focal length of that lens, I can ask. Obviously, there are 2 point sources, so these are real objects. Both the objects are real. Remember that. Huh? And not only that, they can also ask the orientation, that is the orientation of principal axis of possible lens. Because we don't know anything. We know that principal axis is in this plane, but where is that principal axis? Where in the plane? And what is the location? That is not known to us. Now we need to think in terms of the data given, that what are the possibilities we can have, so that these 4 points form the set. Now think. Now it is more of a aptitude problem. How does a student observe the combinations possible? Let me think this way. Let me come up with some ideas, and then I will streamline that. What are the final possibilities? You know? So one thing that is coming to my mind is, if one of them is a possible source and a possible image, so it seems that they are at equal distance. So in my mind, there are a few ideas which are coming up. There is a 2f possibility. I will look into all the possibilities, right? So what I'm thinking is, if he is telling me that that the source, like this is an object kept at 2f, and if I get an image at 2f, then I know that they will be at the same distance from the optical center. Not only that, their heights will be the same. The angles from the optical axis will also be the same. So that is my first observation. One more thing comes to my mind, that if I connect a line between the object and the image, it passes from the optical center, and that is valid for any possibility. Even if I form an image somewhere else, line connecting the source and image will pass from the optical axis. So what is coming to our mind? First of all, let me evaluate about this centroid. So I think 2 ways. If centroid is a source out of 2 sources, either it is a source, or the second possibility is, if centroid is a location of image. Let me first streamline. There are only two possibilities. Under the possibilities, I'll solve. So one source, and so if centroid is the image, if centroid is the source. Now let's think. Let's think. If centroid is the source, then what we are saying is one source is lying here. And because there is a rotational symmetry, if this is S1, then one can write anywhere. So you can treat it like S2. And you can say like these are the two images, maybe here, I don't know. So maybe I1, I2, like I1, I2, one of them. This is a possibility. Similarly, if centroid is the image of any one of them, let's say this is my S1 and this guy is my I1, then this can be S2 and this can be I2 or vice versa. These are the possibilities. If that is my image, I could have now just observe this question carefully. If for any of the sources, image is formed here, so I know that the optical center will be the intersection of those 2 points. Just look into this point carefully and try to tell me that which of them is not a possible structure, because if I draw a few lines, like if I say ki this is a source, let me just explain, even like if I take S1 here just to explain the point, and if I take what S1, I2 here. So I may say that these two guys, optical center, don't you think that in this combination, this seems like this will be the line on which the lens will lie for S1, I1, and this will also be the line where the lens will lie. So this is the location of lens if this is the possibility. And if this is correct, I mean, I could have rotated the system and drawn anywhere, but I thought I can draw one of them. If this is the possibility for the location of lens, these two guys are equidistant. So this seems like 2f kind. I'm not saying this distance is 2f. I'm saying this is 2f combo. I'll analyze afterwards that I'm not saying I have not found out the orientation of principal axis yet. But I know that the optical center is here. If this was a possibility, if optical center is here, then this is equidistant or equiangle also. So these two form that combination. And what about these two guys? No, these two guys are on one side of optical center, one side of the lens. And if real source and image are on the same side for a converging lens, then the image is virtual. And for any combination, now let me draw it like this. For any combination, if this is F and 2F, and you are closer here, one ray which is parallel will pass from the focus, another from optical center will pass undeviated. So we understand we can form a virtual image here. So if this is O prime, I prime on the same side, then it will be virtual, and the distance of image will be more than the distance of object. But you see, there's a contradiction here. There's a contradiction. Because the location of image is closer than the location of object, which is not possible. So that's why I say this is not possible. Now, I streamline my question like this, that definitely that position is one of the source positions, And this is the image. Now, again, if this is the idea, then this line is again one line on which lens will lie. So lens will lie here now, very clear. And S2, I2 combination. So now I'm streamlining. This is S2, I2, and this is S1, I1. And now this is my final combination, and this is my optical center. I know the optical center. I yet don't know the orientation of my lens. So I'll presume something and then I'll derive it. So now if I presume that the lens is at some angle with the horizontal, take some angle alpha. Take this as your principal axis, and let us try to apply the concepts with respect to the principal axis. I don't know the angle here, so I've taken this, that angle is alpha with the horizontal. Now I'm saying, because this guy and this guy is at same distance. So if this is your point object like this, H, this is your point image, we know that this distance and this distance will be the same, right? And let me take few distances. Let's say if L, L, L is given, and I draw these things like you understand. So these distances are like L by root 3, distance from the centroid to the corner, L by root 3, and this distance is also L by root 3. So I'll solve in terms of these parameters. So I know that this angle was taken as, let me take it more simply. If I take that angle, this angle as alpha, my calculations will ease out. So I'll take this as alpha. So not with the horizontal, this is some theta, I'm not interested. But with respect to the line, this angle I have taken as alpha. This taken as I have alpha. So I know that this distance is 2f. So my first equation is twice of mod of focal length, which is your question also. Focal length mod is required. Write it as f only. So let's not write again. So 2f. So 2f is this distance. And that seems to be, this was like L by 2. So L by 2 cos. So L by 2 cos alpha. That is my first equation I'm writing. L by 2 cos alpha. L is known to you, remember. Those distances are given to you. We'll substitute in the final step. Alpha is not known and F is not known, but I've written this. Now, the second thing. Now I will say that with respect to the same principal axis, if this was your source, real source, right here, this was your image. So now let us try to use the fact that for lens location, I'll use the formula 1 by V minus 1 by U is equal to 1 by F for the lens which is kept here, optical center here, and this is the principal axis. And I've drawn perpendiculars for both the guys. Now I have to write V and U values. So observe carefully the distance of this center point to this point. So if you draw this line here, this distance, this black distance is, this is 90 and this is 60 and L. So L root 3 by 2. So I'm saying this distance is L root 3 by 2. And what about that angle? That angle is 90 minus alpha. This angle as such is 90 minus alpha. So my V distance, image distance, is on the same side of the lens. So negative and L root 3 by 2 and cos of 90 minus alpha sin alpha. This is my V, negative of this much. So I just calculated the distance of optical center to the image, which was L root 3 by 2, L sin 60. And I then took component of this on this line, and this was 90 minus alpha. That was perpendicular. This was perpendicular here, right? Because it is connecting the edge to the center point of the equilateral triangle. That was also negative. Fine. What about U? U is also negative. And this is for this point. Now I have to draw perpendicular. So I need the distance from S1. So this black distance was known. Now let me just depict it. Let me just, move a bit up. Let me try to show you what was that distance. So now I am interested in this distance, So I know this value will be equal to, so the angle is 30 here. So it is 1 by root 3 times L by 2. This distance is L by 2. So tan 30 is 1 by root 3. So L by 2 root 3. So this distance is L by 2 root 3. So now what will I get? I'll get minus L by 2 root 3 into cos of 90 minus alpha. So again sin alpha. So fine. We are now close. So if I just substitute all the information, this was my first and this is my second. So technically speaking, I'll just write my second carefully. What I'm getting is 2 by L root 3 sin alpha negative and positive 2 root 3 by L sine alpha. This is coming out as 1 by F. Just write those terms even carefully. So you will have 2 root 3 upon, just solve this properly, 2 root 3 minus 2 by root 3 times 1 upon L sine alpha. That is what we are getting for F. And already L is a known constant and alpha will come from 1. So now what will I do? I'll substitute here that from this equation I got cos alpha is equal to 4F by L. The thing is, I am not making substitutions, so calculation seems lengthy. Otherwise, it may become easy. So cos alpha, cos alpha is 4F by L. Just remember that 4F by L. So I'll substitute here. So I'll get cos alpha is 4F by L. So finally, I should write, what is my equation? 1 upon F is 2 root 3 minus 2 by root 3 into 1 upon L, and that sine alpha is root of 1 minus cos square alpha, which is 16 F square upon L square. Effectively, I have written an equation for all the terms. As L is known, you can calculate the value of F and alpha both in the problem. Yeah, what do you want to say, beta?
We can substitute F, will get alpha in simple terms.
Yeah. So you are saying if you, I think alpha will be very simple. Na? F can be written as L cos alpha by 4. It can be easy that way. L cos alpha by 4. So 4 by L cos alpha would have been, what is this now coming out as? It has 3 into 6 minus 2, 4 by root 3 into 1 by L sine alpha. So alpha is 30 degrees, I suppose. Alpha comes out as that. Because like 4, L. So tan alpha is 1. So alpha is 30. So once you know alpha 30, I think easily you'll get. So the core concept of the problem was, expression I'm writing, it took some time because L was given to you, and once you know the value of alpha, you'll get your result because point sources are kept at a distance. So you understand S1, S2, all that distance was given. So you know 24 in this case is L by root 3. This is given as 24 because the distance between sources was given. So I finally realized that the only possibility is the first one, and then one of the sources at centroid, one at the corner. So L by root 3 is known. So L in this problem is 24 root 3 centimeter. Alpha is known, L is known, so you can find the value focal and you'll get it. Right. Let's move ahead. Let me take another fundamental problem, maybe a bit based on hyperbolic orbit. So if I can use this here, just try to read this problem carefully. And it seems to be like what I will try to do is there are two possible concepts to solve both these problems. So I'll try to use energy method and the hyperbolic orbit also to solve the problem, to derive the relation. So let me take a fundamental problem to make the momentum, and then I will take a better problem. So this is more of a fundamental problem. The problem says that you have got a planet and there is a uniform cloud of dust particles. This is the cloud. This cloud is approaching this planet from a great distance with a velocity v0 relative to the planet. So we are in the frame of reference of planet. Radius of the planet is r, and the escape data, try to note very carefully. Escape velocity from the surface of planet is ve. The question is, if this cloud, now the cloud is like a infinite planar wavefront. It's like a plane wavefront, infinite in size in the YZ direction. Along the x, it has got a length of L, and it is quite distant. So like even the nearest wavefront is at infinite distance, kind of. Length is L, cross-section of the cloud perpendicular is very large. Density is rho. So the question was that when this cloud approaches, how much mass of the cloud will hit the planet? If that infinite size intercelestial kind of cloud is coming towards the planet, what is the maximum mass of the cloud which is going to hit the planet? Now, problem is based on a fundamental concept that basically, because you are starting from a distance which is greater than infinity, you have to observe this cloud as a combination of individual particles. So every particle is going to follow a hyperbolic orbit. And we will first try to observe that limiting particle. I'll take a limiting particle. Just try to observe what I'm going to do. I'll draw it a bit large. Like if this is my planet, right? And from the center, if I got to a distance which is tending to infinity, and in the cross section, if I find out a limiting cloud particle, LCP, which is at a distance of, let's say, small r, then what is going to happen is this guy is going to follow a hyperbolic orbit. Limiting means we are presuming that this guy will just touch my desired planet surface in or orbit in a tangential manner, right? Just touch tangentially with some speed, and more optimally, I should say here, somewhere here, more optimally here, with some speed which is, let's say, equal to v, let me say v. Now, when he started, his velocity here was v0. So if I just apply conservation of energy, just to solve this carefully, if I apply conservation of energy, what I'm getting is this particle is having some mass m, so it was having an energy half m v0 square. The potential energy was 0 there. It reached here. It got a kinetic half mv square. And with respect to this mass of the planet, capital M, the radius capital R, it is minus g capital M by capital R. Very simple equation 1. We also know that when somebody says that from the surface of planet escape velocity is VE, you understand that this term is basically minus negative half mve square. You understand V escape from the surface is basically root 2 g capital M by capital R. I've used it and I have eliminated this because now half m can cancel, and basically V0 square is V square minus VE square. So you start with V. So basically V0 is given, V is given. So you'll find out V. The speed with which it hits is like V square is V0 square plus VE square. So I got this. Now I could have directly said that by conservation of angular momentum, I could have said mass m0, m v0 into r is mv capital R, like m cancels, and what is required? So I get my v as v0 small r by capital R. Simple. Now I had to find out r. My interest is to find out r, so I will eliminate this. So it becomes V0 square small r square by capital R square is V0 square plus VE square. So basically, R square is what I am expecting. So R square by capital R square minus 1 into V0 square is equal to VE square. So you get your term as R square is VE square by V0 square plus 1 into capital R square. And a student says an answer will be, if now by symmetry of the problem, if this happens here, I can draw a disk here, which has got a radius of r. And now what I'm trying to say is all the mass, just all the mass which is present, because this was infinite. So I've drawn a disk here. And now I say in this disk up to this point, everything which is present, right? That is going to hit because everybody is coming from infinity. So anybody at r distance is hitting the surface. So anything which is even at a lesser distance will obviously going to hit. So your answer to the mass should be, because length was given as L. So I should have said it is density into pi into small r square into L. So it should be rho pi L into small r square. And that small r square will be capital R square into V square upon V naught square plus 1. Given all the information, you get the answer. The only thing is, while solving this problem, I knew that the orbit is hyperbolic, but I solved it without using that nature of hyperbolic orbit. Now what I'll do is, that concept which I could have applied here again in method 2, I'll try to use that concept. I mean, nature of orbit can also be used. Just some problem with my laptop. I can use the nature of orbit to solve the other problem, which is better framed problem, where you cannot directly report like this. Now let's see how we think in this problem by energy and by nature of orbit. Now what he does is, now he says there are two particles, spacecrafts, masses M1, M2. They're flying with their engines off. So they are particles for me. And they're in the gravitational field of this planet. And their distance is large than the masses of the spacecraft. That's fine. So they are at infinite distance like cloud. Absolutely similar. Now speeds of the spacecraft at great distances are equal to V1 and V2 respectively. So talk about one spacecraft. His distance at his speed at infinite distances V1. So it's like a hyperbolic orbit with that distance V1. After crossing the star, so it will follow a hyperbolic path with the center of Earth, like whatever, center of star, acting like my focus, and it will go away, and at infinity it will have the same speed. So what I'm trying to say is, if I draw my XY plane, this star is coming from somewhere. It follows a hyperbolic orbit. It comes like this. It goes back like this. So this is the orbit, even in the last problem, like this. And here, sun, like that star and its center is like this point. It doesn't touch it. Nothing, nowhere it's being said. The only thing that's being said is the collision doesn't happen. This point could be tangential also, but the center will act as the focus of the hyperbolic orbit. So, and let me analyze for, so if I say he starts at infinity with V1, so he goes back with V1 at this another infinity. This is the path it adopts. This is the focus here. So what I'll do is, let me use the property of hyperbola here. So I know that if you draw these tangents at infinity, like conjugate axis will come, it will subtend some theta here, some theta here. This coordinate is 0, 0. So I've taken this coordinate is a comma 0. This coordinate here is a e comma 0. And I can draw these vertical lines, right? You understand? So you understand that this point is like a comma b. And obviously here this coordinate is a comma minus b. And I know that in this hyperbolic orbit with origin here, you can write your tan theta as b by a. There are few informations which are given which will simplify the problem. If you observe, they say one thing. They use that angle of 90 degrees. They say that the spacecrafts move with speed v1, first one with v1 and second one symmetrically with v2, and their velocities are perpendicular to the initial direction of motion. So what they are trying to say is, when v1 starts, when this starts with v1 along the tangent to this axis, when it moves to goes to infinity along the second tangent, the direction of this v1 and the direction of this v1, these two guys are perpendicular. They are saying, so let's be very clear about the language. Language is not about v1 v2. Language is like v1 v1 and v2 v2 in symmetrically. So basically he's trying to tell me that theta here is 45 because that tangent and this tangent are at 90. So theta is 45. So basically a is equal to b is in this problem. Simplified thing. Now what I will do, once I know that theta is known to me as 45, I can do all the observations. Like I know that this distance, so everything comes up now. Like this is A, this is A, this is A root 2. So you understand this coordinate is also A root 2 comma 0. You can form a circle with center here. That is A root 2 comma 0. And if this is A root 2, then this distance is known to me. This is A root 2 minus A. So if I start with V and I reach this point of minimum distance with some velocity, let me call that velocity V, then by conservation, conservation of angular momentum, I could have directly said that my initial mv1 into lever arm, like I will drop a perpendicular on this line. So when the particle was here, his angular momentum about the focus of the star is this distance, and the total distance is A root 2, and this angle is 45, theta is 45. So this distance comes out as A. It is like A root 2 sine 45. So A, so mv1 into A, this distance. And when you come here, you pass from this point. This is small m into V into this distance, which is A into root 2 minus 1, into root 2 minus 1. So basically, I'm getting A cancel. What I'm getting is V1, if I write here, is V into root 2 minus 1. Right? This is given to you, V into root 2 minus 1. Now use the same information for the second guy also. So he says, during the passage around the star, the minimum distance of the first spacecraft, that is R1. So basically he's saying that R1, now this is first equation. And secondly, I can say that R1 which is given is basically A into root 2 minus 1. A into root 2 minus 1. Now what I'm trying to say is, if you can find out that relation, secondly, I can conserve the energy and write the equation. So by energy, I can say, so hyperbolic orbit I've used. R1 is known from these two equations. For a given A, I need to eliminate this term A because, like, for the second spacecraft, A will change, right? The features are the same. So somebody can say, sir, fine, I wrote my equation. I got half mv1 square. I came to the nearest point. I got that velocity as half mv square, which you can write in terms of v1. And then there's that term, which is minus g m divided by that distance r1 here. Now m cancels out, and just look into the carefully look into the pattern. There's a pattern. v1 square minus v square upon 2 is minus gm upon r1. Now I'm saying every time v square minus v1 square is 2gm upon r1. This is a constant for the second one also. R1, R2 is something which we need to find out. Just observe v square minus v1 square. V square minus v1 square in terms of v1. So write v as v1 upon root 2 minus 1. So basically you will get v1 square as common in this equation, and 1 upon root 2 minus 1 the whole square minus 1 is a 2gm upon r1. Now tell me one thing. If you carefully observe, you can easily say that if I derive this for second one also, this 2gm, the only difference that will come is there also the angle is 90. There A will become a new A, right? V1 will become V2 there. But I'm very convinced directly by concepts, by symmetry, that V2 square into the same constant will be 2gm upon some prevalent distance R2 there. And then it's a simple division of those two things. So V1 square upon V2 square will be equal to R2 upon R1. So the answer to the question is, he said, what is the minimum distance R2? So R2 is R1 into V1 square by V2 square. That is the main thing which you can answer, because I used momentum, angular momentum and energy, and just a fundamental idea of this hyperbolic orbit. And I strongly believe that when they will put up this question, this is definitely on the lines, because they can always use this idea. One question in the test has come on elliptical orbit. So I wanted to analyze this problem on another concept. So this is hyperbolic. And because energy of the system, when it is starting from infinity, that is positive. Negative energy, you will have an elliptical orbit, and for zero, you will have a parabolic orbit. So they can always use the idea of nature of orbit to ask some question. Let me just take care of a few more if possible. This is one very nice question on mechanics, and it uses a bit of concept of SHM also. So like combination of oscillatory motion and force concept, both. Read the question carefully. Here there is a cobweb. So there's a cobweb thread. So you understand it has got elasticity. It is having a negligible relaxed length. This is important. So the natural length is 0. It is stretched between 2 points, A and B, on opposite walls, and gravity is present, like G is present, right? We are in the vertical plane. And he has taken a massless cobweb. It is not having any mass. So it is a massless, stretchable string. And I mean, if you look into this cobweb thread, basically is talking about a massless spring or a massless stretchable elastic string and having a negligible natural length, right? Negligible natural length. That's what he's saying. So theta is given, this is given, and everything is fine. Now he says, in this state, the thread makes an angle of theta with the horizontal. And its length and force, like length and force constant K is given. We will definitely use it further. That will be required. Now a spider is there, and spider is having a mass of M. Now this spider crawls gradually from end A to end B. So he's moving slowly. Now remember, when he will move slowly, the shape of this thread cannot remain the same. It is going to change. So that is the interesting thing. The shape is going to change when he will crawl from A to B. Now representing your X and Y like this, and this is your origin. So if this is my X axis, this is my Y axis. The question setter is saying that when he will crawl, what will be the equation of the path followed by the spider? Very interesting form. And you can assume that Hooke's law, like F is equal to minus Kx, is valid for the given thread also. Now, I'll give you a few basic points. So what I will say, just as he starts, it seems that this point dips down, then he moves up, the angle of dip changes. So what I perceive is, at some general point, this thread will have a general shape. And I will, my spider will be at a general point X, Y. In fact, when you will observe the answer, it is a very beautiful path that it follows. But the proof is like quite complicated. So, and the second thing is why I have presumed these lengths to be like straight, because the string itself doesn't have any mass. So string cannot have a curved shape. With respect to this point, there will be a critical point here. But these are straight lines. But I don't know the length of this line L1. I don't know the length of this line L2. I don't know the spring constant of this line K1. That is more interesting. I don't know the spring constant here, which I'm treating as K2. K1, K2, R1, R2, whatever it is. I know the coordinates. Now, I will take some angle, alpha, beta, to start the problem, and then we'll see how to approach. So I'll presume that this angle here is alpha, and this angle here is beta, and this guy is sitting here, so he's having a weight mg. So because he's crawling slowly, maths, like NLM equations, are very simple. Somebody will say that force will come from this side, force will come from this side. So let me call it as F1, F2. That is simple. So F1 cos alpha is equal to F2 cos beta. And I can say F1 sin alpha plus F2 sin beta. That will be equal to mg. One more thing. This distance is L sin theta. And remember, if I write this distance, this is minus y, because I've taken coordinate at xy and I'm in the fourth quadrant. So y here is negative, so distance is minus y. So I can write the third equation by geometry, that tan beta is coming out as L sine theta minus y divided by this distance, the x distance, right? And that can be written as L cos theta minus x. And similarly, I can write tan alpha is minus y upon x. So these are the fundamental equations for x and y. So basically, I'm saying that x and like alpha and beta can be eliminated from these equations. That's not a problem. And your expectation of answer is in terms of y versus x is what you expect. And your answer can contain theta. Your answer can contain g. Your answer can contain mass m, L, K. So these are the constants I can have in my answer: m, g, k, L, and theta. So I said fine, x, y, I can. So alpha, beta is eliminated. So now the crux. How will you write F1 and F2? If somebody can write F1 and F2 properly, he is done with the problem. Now I'll just show you the calculation here, because I've just scribbled something to help you out instead of solving it slow. I'll just go through the solution immediately so that you can understand that small calculation. Some scribbled content, if I have got here, maybe I can complete, because that is a lengthy calculation. Just let me see if I have, yeah, just observe this page carefully and finish off this problem before we leave. There are a lot of calculative steps. Observe. Here I have written few equations. Just observe the same diagram. All these geometrical parts we have done. I think if it is visible to all, if I can. Yeah. So force balance is fine. Just observe this equation carefully. After taking all these terms, I need to write an expression for K1 and K2. So what I've done is, I've used the basic concept of springs in series. So I'll write 1 upon K1 plus 1 upon K2 is equal to 1 upon K. That is my first equation. Now, how will you substitute K1 and K2? So I've written a relation here. K1 into this X distance. Because if you look into, like when you have written K1 into R1, you remember F1 can be written as, because he has said the natural length is 0. So if this string I have taken length as L1 or R1, whatever I've done here, K1, the F1 that I am writing in my problem there is basically K1 into the extension in this spring, and that extension is basically its length. So you can simply write K1 L1 or K1 R1 in this derivation. And simply F2 can be written, if this length I have written as L2 or R2, F2 can be written as K2 R2, K2 L2 or K2 R2. And just observe carefully that when I have balanced the forces in the horizontal direction, because F1 cos alpha was being balanced with simply F2 cos beta. I have just used my scribbled page. So now that K1, this term becomes K1 L1. So K1 L1 cos, so K1 X becomes K2 L cos theta minus X. Simply, that's what I've said. Because this guy becomes K2 L2. L2 is and R2 is same in the diagrams. Don't get confused. K1 X is equal to K2 L cos theta minus X. And I've assumed this constant as something and I've eliminated the constant. You understand this? So I assume this constant is something. I've substituted here. I got my constant as scale cos theta, and I've resubstituted that constant again now to solve the problem. So calculation you can do on the previous page. I'll write that equation. And then it was just simple. Like, I think if you get this point where I'm solving my problem, you understand that this guy is K1 into his length L1. This guy is K2 into his length L2. But if you substitute in first, so by first and fifth, I'm getting K1 L1 cos alpha is X, is K2 L2 cos beta, that is horizontal distance, L cos theta minus X. That is known. And one more sixth equation I have used. and 1 upon k1 plus 1 upon k2 is 1 upon k. Basically, then I said use 1 and 5, this equation, let's say 7 and 6. So by 6 and 7, you will eliminate k1 and k2 in terms of x and y. Then simply substitute them here. This f1 is k1 l1. This f2 is k2 l2. Now I've written everything on the board. Just do the substitutions and derive y versus x in. So it's like assignment for all of you. Go through the slide and you'll get your answer. I'll have to finish off. I have to rush for another lecture, which is there. I'll see you in the next class and go through these concepts carefully. You can also access to my video and see.
Sir,
Can we discuss in the next class? Because I just have to rush. I've taken small point. If you want, you can ask. Yeah.
yes, small point, sir. Just
Yeah.
we go in that triangle of sources, sir. That light are arranged in the triangle.
Yeah.
That problem.
Yeah.
In
What
that
is the
problem,
concept?
in the problem, how did you get cos alpha is equal to 4f by L, sir?
How I got cos alpha? I'll just try to show you if possible.
I
Yeah.
lost my internet connection that time.
How I got cos alpha is equal to 4f by L, right? You got this equation. Twice of f mod is L by 2 cos alpha. And how I got twice of f? I said this distance, because the distance of source and image are equal from the lens, so that will be 2f only. So I said this distance is 2f because the distance can be 2f along the principal axis. So if this is the axis, principal axis, and here is an object and here is an image, so along the principal axis, the distance from the optical center will be 2f. So I just took alpha and this was L by 2. So I got this distance is L by 2 cos alpha and this is also L by 2 cos alpha. I said that is 2f. So I think you'll get your answer. Right. Okay, students, see you in the next class. Take care. Bye-bye.
Thank you, sir.
Bye.